Right. Ed, could you check for me? All right. All right. Okay, so um, we've been talking about we talked about public key crypto, what it's good for. It's good for securing and signing. And then we talked about, we're getting into how does it work. But to help you kind of really, uh, to kind of figure out how it works, we're going to, we looked at this ice cream van problem. All right. Okay. So we're back from the break. We now understand the ice cream break problem. We understand that it's difficult. It's hard. It just happens to be easy to check and easy to make this game. But it's actually kind of hard to play this game. All right. All right. How does this help us with public key crypto? Let me show you a couple of very simple public key ciphers. The first one is not a real public key cipher, but I hope it'll help you appreciate how they work. Okay. The first is just an example, not an actual cipher. The second one will be an actual cipher, just an older one. So the first example of a public key crypto we're going to look at is going to be this graphical example of encryption. It's not an actual encryption scheme as far as I know. All right, but here's a graphical example. Let's say that I have this number that I want to encrypt, the number 66. All right. I want to encrypt this number. How do I do it? Well, the public I'm going to encrypt it with a public key. I'm going to decrypt with a private key. The public key looks like this. The public key is a graph. It's a picture. All right. Then what you got to do is take 66, break it into as many numbers as there are nodes on this graph, and just put those numbers anywhere you want. Okay, so 66, I can break it down into this like 3 plus 2 plus 1 plus blah, 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 blah. And then I can just put those numbers anywhere I want on the graph. It's not encrypted yet because anybody could just add these numbers up and get 66 again. So it's not yet encrypted. Okay. Now, the next step, the encryption step, is this. At each node, simply add the value of that node and all the connected nodes together. So for example, this node on the top right, whose value is 1, we sum up 1 plus 8 plus 3 plus 6. All right, and then we've got 18 at that node. Got it? You do that at every single node. The one on the bottom is 6 plus 1, 6 plus 1 plus 4 plus 11. So we've got about 22. Now, you forget where you put the original numbers and you just leave the sums at the nodes. Ta-da! That's your ciphertext. That's the encrypted um, number. The number 66 is encrypted into a graph form. Okay. So this is a graphical view of this encryption scheme. Let's look at the graphical view of the decryption scheme. Okay. Now, why is this an encryption scheme? Because you don't know how to add these numbers together to get 66 again, right? Like which of these numbers would add together as 66? It's a little hard to tell. All right. So, how do we decrypt it? To decrypt it, we go to the next page. We start with the cipher graph or the ciphertext, and we now go to decryption. The private key looks like this. It's a similar graph with a couple of big empty circles in there, like 4 big empty circles. Okay. You basically look at this ciphertext. You can ignore all the numbers except the numbers that belong to the nodes of these 4 nodes that the private key told you. Okay? And now you sum those nodes together and you got 66. You can ignore the rest of the information. Cool. How did that work? It worked because it's the ice cream van problem. The ice cream van problem aggregates information from adjoining nodes. If you can find a minimum set of adjoining nodes that captures information of the whole graph, you've got all the information. All right. Is that clear how that works? So to encrypt, split a number like 66 across all these nodes, sum them up. sum them up where each node is summed by its neighbors, okay? It just so happens you don't need all these sums because a limited set of nodes actually capture all the neighbors. It captures all the information anyway, all right? You just sum those up and you got your decrypted number back. Is it easy to decrypt this? Well, on pen and paper, no, it's not easy, because what you would have to do is you would have to take this public key and play the ice cream van problem on it, which, as we found out, is not easy. I mean, for a small game like this, it may not be too difficult, but for a large game, it would be difficult. If instead of, what is this, about 16 nodes, if we had 1024 nodes, this would not be feasible for a human being to play in real time, forget as much time as they want. Okay? So the only way to hack it is to play the ice cream van problem. So do you see how the public key and the private key work? The private key is the solution to a hard problem posed by the public key. To get the private key, you would have to play the hard game. All right? But they actually have the same information. So this is just an example of how private and public keys are related. They're related because one is the solution to a hard game, the other is the problem statement for the hard game. All right? And we can use these two together to create things that are hard to crack, but if you know the solution, it's easy to verify. It's easy to resolve. All right? So this is the secret behind public key cryptography, or asymmetric key cryptography, which is we create keys that are based on hard games, if you will, on hard problems. All right. What is a hard problem? Well, there's many mathematical problems out there that are considered hard. I'll show you maybe an example of one or two briefly, not in much detail. But to give you an idea, we believe there are out there certain mathematical problems, some of which we know, which are considered hard, and we technically we call them NP hard. All right, the NP stands for non-polynomial time. It's just a non-deterministic polynomial time. It means that it would take an extraordinary amount of time to solve these problems. It's not that they're unsolvable. It's just that the time it would take a computer to solve it would be so long that the universe would have died by then. All right. So these are extremely difficult mathematical problems. They're just so complicated to solve. The ice cream van is a baby version of something like that. It's obviously not that difficult, but it could become quite difficult for human beings, but not for computers, perhaps. Okay, but there are some problems that are so difficult that even a computer can start solving it. It can solve it, but just not in the time frame of this universe. Right? It would just take too long. We call those problems NP hard. They are really hard to solve. Computers cannot solve them. Okay. And they are distinct from P. P is problems that are easy to solve. So we don't want these problems. We want NP hard problems. Okay, to generate public key asymmetric key ciphers. However, even though we want to use hard problems, we need those problems to also have solutions that are easy to check. Okay? If they're hard to solve but easy to check, we can figure out a way to create a nice, interesting game to create a public and private key. Okay? So that's what cryptographers are looking for. They're looking for math problems that are NP hard to solve, and yet they are easy to check. Easy to check is sometimes called NP. All right? A computer could solve it quite quickly in reasonable amount of time. A human being maybe could not, but a computer could solve it in a reasonable amount of time, microseconds. Okay? We want problems that are NP hard and NP. Such problems, the intersection of NP hard problems and NP easy to check problems, is called NP complete. These are problems too hard to solve, but with solutions that are easy to verify. All right. So a lot of asymmetric key crypto uses mathematical problems that are NP complete. All right. Now I have to tell you a couple of problems with what I just said. One, One problem is that there are some problems that were NP hard, but now with the advent of quantum computing, there may not be that hard anymore. Not all of them, some of them. So, but quantum computing is not as big a threat as people think because there's plenty of enough NP hard problems that quantum computing cannot solve anyway. So we just have to be careful which problems we pick now because quantum computers can solve some of them in real time. So that's one issue. All right. But that's not even the biggest threat. There's a bigger problem, and it's one that we cannot resolve. And that's this. Remember, I told you that there's problems that are easy to check. If you look at the diagram I showed you, it looks like there are problems that are easy to solve, and all problems that are easy to solve, called P, they're also easy to check. Right? We believe that. All problems that are easy to solve are also easy to check. However, I am presuming that there are problems that are easy to check, but they're not easy to solve. All right. So I'm assuming that there are problems that are easy to check, but they're not easy to solve. And some of them might even be hard to solve. Okay. However, we do not, to this date, have a mathematical proof of this. It is entirely possible that all problems that are easy to check are also easy to solve, in which case the picture would look like this. And we would not have any NP-complete problems. As far as we know, there are problems that are NP-complete, and I'll show you a couple. But we don't have a mathematical proof that that is how the world works, how the universe works, okay? We are hoping that there are problems out there that are NP-hard, that are easy, that are, also NP-complete. But we don't know this for a fact. So this problem in mathematics, and is considered, I believe, one of the most enigmatic and most important unsolved problems in mathematics, is to ask, is P equal to NP? Or more clearly, to prove that NP is not equal to NP, to prove that this set and this set are not the same. We don't have a proof of that yet, okay? So everything I show you today and everything we've done for the last 30 years assumes this picture. We don't have a proof of it, all right? If you follow the news, almost once a year, there is some mathematician who's like, I solved it. I can prove to you that it is or is not equal. And then it goes for several months and people say, there's a problem with that proof. And then next year, repeat, oh my God, I found a solution. So you'll find something, all right? All right, so I just want to say this is how these public asymmetric key ciphers are working, okay? Now I call them asymmetric key because there's two keys that are not the same. I sometimes call them public key cryptography because how we use these keys, the practice of using these keys, is to keep one public and keep one private. But for the most part, I'm referring to asymmetric key as public key because I'm assuming one is private, one is public, okay? Right. Let's take a look at an actual public asymmetric key cipher, public key, private key cipher, okay? Now, I'll tell you that this was an actual cipher. It just got cracked many, many years ago, all right? But maybe in the early parts of the Cold War, like in the, I don't know, 70s or 80s, it might have been used for some time, but it is no longer used because somebody found a shortcut. Oops, all right? But let's show you the problem. The problem is called it's called a knapsack cipher. Knapsack is just a very old English word for shubao, backpack, all right? It's a backpack problem. What is the backpack problem? How many of you go shopping with your backpack? Anybody go shopping, like you go to A-Mart or you take a bag with you? You do? Okay, I'm only talking to you. The rest of you can take a break. Okay. Billy, you? You do. Okay, great. So if you're like me and you did all your shopping and at the cash out at the cashier, they scan everything and you have to pay. And then you have to take your backpack and put all the things into your backpack. If you're anything like me, and I think we're all human beings are all similar, you're trying to find the optimal way to put everything into your backpack. It's like a Tetris game, right? You're like put this in, left in. No, wait, no. Oh, I found a better solution. You're trying to find a way to make everything fit perfectly into your backpack so you don't have to carry anything in your hands. Do you do that? Not really. You buy a new backpack. All right. So trying to fit things in perfectly in a volume is the backpack problem or the knapsack problem. Okay, we all play this game somewhere. Even if you don't use a backpack, if you use a shopping bag, if it's a paper shopping bag, you still play that game, right? You're like, oh no, take the milk out, put this in first, blah 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 blah. There's a mathematical version of the game, and it looks like this. All right. Let me show you this one. All right. So I've got the number 548, 548. Okay. Now I need to break it up, and well, it's already broken up for me. You see all these numbers here? It's already broken up for me. However, I don't need all these numbers. I just need some of these numbers. So the numbers I need to put a 1. I need to give it a weighting of 1, a coefficient of 1. If I don't need it, I put a coefficient of 0. 0 will multiply to 0, right? So I just have to figure out which of these is going to be 1 times the number, which will be 0 times the number, such that the numbers that remain with the 1 will add up to 548. Would you like to play this game? Why not? Maybe you've seen, I've written up here, this is an NP hard problem. Okay. It's actually ridiculously difficult to solve this problem. For the shortage of time, I'm not going to solve it now. But how would you try to solve it? This goes back to Bijan's question. Where do you begin? That's the problem. Where do you begin? Do you start with the number 82? You can start adding stuff up, but if it doesn't exactly become 548, which one do you remove? It becomes a huge pain in the butt to figure out which ones stay, which ones don't stay. All right. This is the backpack game, the knapsack's mathematical version of the backpack game. Okay. However, take a look at this game. This is another backpack game, this time the number 193. All right. This one I'm claiming is P. It's easy to solve. Would anybody like to try to solve it? Take a minute. Try to solve it. How would you begin? Where would you begin? Think about that and try to solve it. I'll bet you can solve it. Let's do it together. Anybody want to tell me where they would begin? What's that? 120? Why not start with 2? Yeah, if you put a 2, well, you don't know what goes next because like everything goes in. If you start, well, why not 251? Because that's clearly bigger than this number, right? 120, okay. Okay, now you've done 120. How much remains? If it was 190, okay, let's work this backwards. 120 minus 193. Somebody do me the favor. What is it? 100 173. Okay. Oh, excuse me, 73. Okay. So 120 fits. So we have 73. All right. Let's get a marker. So we had 193 minus 120. So that gave us 73, right? Minus 57. How much does that give us? 16? 1 6? Okay. And which number next? Oh, 30 does not fit. So 14 fits. I'm going to circle the numbers that fit. Okay. Minus 14. This gives me 2. Oh, and then 2, right? So the numbers are 120, 57, 120, 57, 14, and 2. All right. Was that easy? That was easy. I think a middle schooler could solve this problem. Maybe elementary schooler kid could solve the problem. Interesting. They're both backpack problems, but one is very easy to solve, one is very difficult to solve. What makes this easy to solve? It's not a general backpack or knapsack. It's called a super increasing knapsack, where every number, let's take the number 3, is not only bigger than the one before it, let's take the number 7, is not only bigger than the number before it, is bigger than all the numbers that come before it added together. 7 is bigger than 3 and 3 plus 2. 14 is bigger than 7 plus 3 plus 2, so on and so forth. If you set up a super increasing knapsack, it's super easy to solve. All right. It's just that if you don't have that property and you just have some general numbers, it's exceedingly difficult to solve. You've just got to brute force it. All right. So I will show you in a moment that you can use these two knapsacks to encrypt and decrypt. But let me just briefly, and I'm not going to go into the math of this, tell you that these two knapsacks are actually related to each other. They're actually related to each other. How? First, to generate these, you first start by creating a super increasing knapsack. All right, that's easy to do. Anybody could create a super increasing knapsack, right? Just like anybody could create this problem by starting with the solution first, right? So you start by creating a super increasing knapsack. Anyone can do it. Just start writing down some small numbers, add them up, make sure the next number is bigger than all the previous numbers added up. That's easy to do, right? Everyone with me so far? Then you pick two prime numbers, any two prime numbers, where the second, well, one bigger than the other, a smaller number and a bigger number, any two prime numbers. Then you find something called the modular inverse of the smaller number. I won't go into it, but it's essentially the number such that if you took m, multiplied it by that number, and then did modulo the second number, your answer would be 1. Okay? That's called the modular inverse. The answer happens to be 12. All right? A computer can solve that pretty quickly. Now, with this number in hand, which we call, okay, with this number in hand, you keep that number, okay? And now the private key will be the simple problem, the super increasing knapsack, and this modular inverse. That will be the private key. We've got to create the public key, which will be the hard knapsack, the general knapsack problem. To create it is super simple. You just take every element in the super increasing knapsack and you multiply it by the smaller prime number. And then you do modulus the second prime number, the bigger prime number. All right? And that will give you this super increase, this general knapsack. All right? So as you can see, we've got a private key and a public key. The private key is a simple problem to make. Anyone could make it on paper even by themselves. And the modular inverse, which a computer can do for you quickly. And the public key is the super increasing knapsack times a small prime number modulo a big prime number. That's it. All right? Private key, public key. How are we going to use them to encrypt and decrypt? Let's take a look. Next page. So encryption. Let's take the number 150 and we want to encrypt it, okay? Finally, a Rail cipher. First, convert it into binary numbers. 100101110. All right, that's the number 115 binary. All right. To encrypt it, you simply place these bits as the weights or coefficients of the general knapsack, the public key. All right. And just those bits, 1 0 0 1 0 1 1 0. All right. And if you now, the zeros cancel certain numbers out. If you add the remaining numbers, you will get another number, 548. That's your ciphertext. You've now encrypted the number 150 into the number 548. All right. How do you decrypt it? To decrypt it, you take the private key, which is the super increasing knapsack and the modulo inverse. And you once again have to find a modulo inverse of the number 548. That gives you 193. 193 is the solution to your super increasing knapsack. All right. Now you find out which bits of the super increasing knapsack add up to 193. It happens to be 100101110. It's the original binary number that you encrypted. All right. That gives you 150. So I know I ran through it very quickly. The key elements are this. We have at our hands a possibly NP hard problem, okay, called the knapsack cipher. What we do is we start with the easy version of it, and we use it to generate a really NP hard problem out of it. The easy version is our private key. The hard version is our public key. All right. And you can play through it. You can play with it yourself later to recreate this. You use the hard problem to encrypt. You use the easy problem to decrypt. All right. This is the basic idea of asymmetric keys. All right. And I know I said private and public. Let's just pretend asymmetric. This is the idea behind asymmetric keys. Okay. You have a hard problem and a simple problem, and they are the same. The trick is you use the simple problem to generate the hard problem. All right. So this cipher was actually used for many years, and when did we stop using it? Let's take a look. Knapsack cipher. I know somebody who knows the answer. All right. The Merkle-Hellman knapsack crypto system. And let me just kind of zoom this up and let's read this together. It was created in 1976. The idea was created. As time passed, they proposed a version of it, blah, 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 blah. Within a couple of years, they had a much better system, but this was an early system. I want to see how soon did it get, like, did people find a shortcut to it? In 1984, a shortcut was discovered to kind of solve this problem by Adi Shamir. All right. So it went bye-bye. Luckily, but before that, already other systems had been created. All right. Oh yeah, a polynomial time attack was published in 1984. So within a few years, within several years, within 6 years, it got hacked. It got cracked. Okay. Adi Shamir is an interesting name because the person who cracked it, the S, is an Israeli cryptographer. The S, his last name Shamir, the S is the S in RSA, one of the most widely used asymmetric key ciphers that is still used to this day. All right. In fact, I'll show you a little later where you've already used it without knowing that you've used it. All right. And So the knapsack cipher, cute little problem, quite easy to set up, quite easy to understand. However, it got cracked after 6 years. Shamir and some others, I think it's Revesh, Shamir, and Adelman, they came up with another cipher called the RSA cipher, which till today is believed to be quite secure, but there is some threats to it. Let's check the news. RSA cipher. This is, I believe it's been in the news almost lately. RSA. I thought it got cracked. Not that it got cracked, but it's under threat. Um, there are some threats that possibly systems like quantum cryptography could break the RSA cipher. What is the RSA cipher? I'm not going to go into it, but the RSA cipher, like the knapsack cipher, is a mathematical problem. But rather than using like some kind of arithmetic sum, it's using powers. All right, it's using uh, numbers raised to other large numbers. Okay, and there is again a hard problem, an easy problem, and they have used this to kind of create a cipher. Okay, I won't go into the details of the RSA cipher, but it's another mathematical problem. In this case, they use like powers of numbers to create. Basically, you have to take a very big number and figure what its factors are. So not how does it, not which numbers sum into it, but which numbers multiply into that number. Okay, so you have to kind of factorize very large numbers. Anyway, so this is the RSA cipher. I will not go further into it. All right. So, and it's still used today. It's used in a lot of systems to this day, the RSA cipher, among others. Okay. I just want to take a pause there and say, I think we have now covered the basic idea behind asymmetric key cryptography. It's cool because you can secure information and you can sign information, depending on if you're using the public or the private key to encrypt or decrypt. Okay. Moreover, we have seen a quick and very baby introduction to how these ciphers work by showing you that they're largely mathematical problems which are NP complete. They're hard to solve but easy to verify given a solution. So we start by generating a solution from which we generate a hard problem. The solution, the easy problem, becomes your becomes one key, and the hard problem becomes the other key. All right. Any questions in general about this before I ask a question? Okay, I've got a question. Did you have a question, Ed?
Yeah, I just noticed from the little quiz you gave us that when you ask about the order, isn't this pretty much not used anymore?
Which one? This one?
Before that, when we were talking about public and private keys, we're doing the order matters.
Okay. Yeah, I've only talked about how to encrypt, decrypt. I've not talked about how it's the configurations in which it's used. Um, but what is your question? So this one, right? So what is your question?
I think you gave us a reading on this, and one of the guys was saying that this is highly not used anymore.
What is not used?
What's it called? I think it has a little. It was called encrypt and then crypt or something.
Oh, that was for symmetric key ciphers.
Oh, okay.
That was last week. That was for symmetric key. There's a similar issue in symmetric key where the order in which you do certain things, when you produce the hash, do you hash the plain text? Do you hash the ciphertext? Do you hash, what do you hash? So that was a different problem. Okay, yeah. All right. Thank you, though. All right. I have a question. If this is so amazing, do you like it? Do you think it's amazing? I think it's amazing. Do you think it's amazing? It's amazing. If this is so amazing, why did I waste 2 weeks of your life to teach you symmetric key cryptography? Why didn't I just jump and show you this? Because it can do everything. What's that? You should learn this too. Learn the history. This is not the history of security. But there is something else. Let me I'm going to try encrypting and decrypting using a symmetric key cipher and using a public key cipher. Okay, I'm not going to use RBNSCL because RBNSCL, as you know, has many layers of things built onto it. I just want the basic cipher. Okay, I'm not going to use it the way you're supposed to use it. I just want the basic cipher. All right. So what I'm going to do is Unix computers come with OpenSSL, which contains some ciphers already. All right, it's a Unix library, and I'm going to take this plain text, okay, and I'm going to be encrypting and decrypting it 100,000 times. I'll be encrypting and decrypting it. For symmetric key, I will use AES. Oops. I will use AES. I won't go into the code for it because it's a freaking nightmare. Um, and for public key crypto, I will use RSA. Now, AES and RSA are both pretty much mainstream ciphers for symmetric and um, asymmetric cryptography. We know that DJ Bernstein doesn't like them, but they're mainstream. Everyone uses them, okay? Now, I'm going to benchmark how long it takes to do 100,000 encryptions and decryptions of AES versus 100,000 decryptions of RSA. You ready? Okay, let's take a look. Oop, AES is done already. Crap. AES got 100,000 encryptions and decryptions done in about a tenth of a second each. I mean, 100,000 and 10 decryptions, 100,000 in a tenth. RSA, it took 2.5 seconds to encrypt 100,000. The decryption is still going on. My point being, if I want to stream a Netflix video encrypted, I don't think I can use public key cryptography. Like if I have like streaming content. Like if I just want to send you an email, that's fine. But if I want to actually, and as long as it's not a big email, as long as it's a small email, it's fine. But if I was trying to send you a book chapter or a book, a PDF or a movie or something, I don't think you would be decrypting. You wouldn't be able to watch it in real time. All right. The fact is that public key cryptography is extremely slow. In fact, oh, there you are. It took over a minute. In fact, it is unusably slow. Boo. You guys got so excited. Like, we're going to do everything with public key, private key. You can't. It's too slow to encrypt data with it, like meaningful data. Okay. Little bits of data, fine, but not big amounts, not even moderate amounts of data. You cannot actually use it in real time. Stephen, are you disappointed?
I think so. We can just use it as symmetric to deliver the symmetric key.
Ta-da! And that, my friends, is the solution. Exactly right. So what we do use it for is we don't encrypt data with it. What we encrypt with it is we encrypt the secret key for symmetric key cryptography with it. So back to the beginning. Yeah, I gotta use that. Back to the beginning. How do we encrypt data? We use symmetric key cryptography. We always use symmetric key cryptography to encrypt and decrypt. All right. So you take it, you use a symmetric key. Where does a symmetric key comes from? You just randomly generate it, right? You encrypt and authenticate it like we did with RB and SEL. You do authenticated encryption. However, and on the other side, they validated and decrypted with symmetric key crypto. However, how do you send the symmetric key to the other person? Asymmetric key cryptography. This is the key. The symmetric key itself is small. It's what, maybe just 1,000 bytes big. Maybe it's just 1,000 bits big, right? It's maybe just like it's a kilobyte at most. It's the symmetric key is not very big. So once we've generated the symmetric key, what we do is this. Well, first, Alice meet Bob. All right. Alice and Bob have to first exchange public keys. They have to first have private keys and public keys, and they have to exchange their public keys. All right. How do they do that? I'll get to that later. That's still a problem. How do you exchange the public keys? All right. Um, but imagine you can exchange public keys with anybody. It's public after all. Okay. So they have each other's public keys. What do you do? Well, if Alice wants to send a message to Bob, Alice first generates a secret key using her computer's cryptographic random number generator, which we now know uses like Cha-Cha 20 or something. It uses one of DJ Bernstein's algorithms to create that secret key. All right. And once she's got the secret key, she first goes ahead and starts encrypting it. But at the same time, what she can do is this: she can sign the secret key using her private key and then encrypt it using Bob's public key. All right, bless you. And then she sends this encrypted symmetric key. I'm drawing a Mac block on it. You don't really need to have one, but you can have you can hash it as well to make sure it's not been tampered with. All right. She's when she sends her authenticated encrypted message, like we did last week, ciphertext plus MacBlock plus nonce. Along with it, she sends the encrypted symmetric key. Excuse me, the signed and encrypted symmetric key. Bob can now use his private key to so the signed and encrypted symmetric key goes to Bob. Bob first decrypts it with his private key and then verifies the signature using Alice's public key. Okay? And that gives him the symmetric key. And then Bob goes back and uses the symmetric key to do the regular symmetric key cryptography. Ta-da! Right? For anybody who's ever been in a communication where they say, we're going to use asymmetric key crypto, you've been lied to. You do not use asymmetric key crypto to communicate data. All it's used for is the key exchange. To exchange the key, and then you fall back into symmetric key cryptography for the actual data. All right? Though interestingly, a lot of security products out there don't tell you the user all these details. They just say, we're going to use asymmetric key crypto to do to secure information. No, they're not. Okay, no, they're not. All right, cool. Whew. Cryptography is not what you thought it was, is it? In the beginning of the semester, it's not quite what you thought it was. All right. How can we actually use this in our code? Enter DJ Bernstein. He's made it life really easy for you. All right. RBNACL, or actually he made NACL. NACL comes, what did we look at last week? Last week we looked at something called secret box and simple box. This week we will look at something called box. Okay, just called box. And the way it works is this. First of all, Alice and Bob have to install Ruby. I'm kidding, okay. All right. And they have to generate private keys and public keys. All right, no problem. And then they have to exchange their public key. So each other has each other's public key. RB and SEL can do that for you. It's so cool. You just call RB and SEL and say, generate a private key for me. That's the easy problem. Then you say, from the private key, please generate a difficult public key for me. It's your public key. All right? Bob does the same thing on the other side. So RBC and SEL, you generate a private key, and then you use that private key to generate a public version of it, the twin of it, right? So that's why I said the keys are born together. They're not two random keys. They're created together. Then on each side, they have to set up a box, RBNSCL box. How do you set up the box? You set up the box by basically providing it the other person's public key and your private key. All right? And that creates a box. Bob does the same thing on the other side. Bob uses Alice's public key and Bob's private key. Okay? The secure communication is easy. Only thing you've got to do is once you know the message you want to send, you've got to create a nonce. And then you call your box and say, please encrypt this message with this nonce. Okay? The nonce is used for the symmetric key cryptography part. The nonce is used down here for the symmetric key crypto, not for the public key. So box, this NACL's box is actually a hybrid. It does public key, private key, and symmetric key. It does this whole picture I just showed you up here for you. You just have to create a nonce by yourself. All right. All right. So then to encrypt it, you create the nonce, and then you say, take the box object and you say, please encrypt this message with this nonce, and you've got your ciphertext. All right. On the other side, Bob needs your nonce. You have to send the nonce to Bob. The nonce is not a secret. You can just send it. And Bob calls Bob's own box, NACL box, and says, please decrypt this ciphertext with this nonce, and they get the plain text back. All right? Now, if you don't even want to create the nonce yourself, you're in luck. Let's go back to simple box for a second. Simple box. Let me jump to code. Simple box, simple box, simple box. All right. So this is how simple box works. We require RB and SCL. Alice excuse me. I'm being Alice and Bob at the same time. So Alice creates a private key and a public key from RBNSCL's private key generate, and the private key can generate a public key. Bob does the same thing. Bob generates a public key and a private key. I assume they don't keep changing those. They have done those a long time ago. Okay, they just need to exchange it. So once they exchange public keys, Alice goes ahead and creates a box using Bob's public key and her private key. Bob does the same thing. Bob creates a box using Alice's public key and his own private key. Now, simple box is simple. By the way, you notice this time I'm not using box, I'm using simple box and saying from key pair. Okay. Now, Alice signs it by just calling her box object and saying, please encrypt this message for me. Simple box will even create the nonce. And Bob decrypts by simply calling his own box and saying, decrypt the ciphertext, and the secret comes out. All right. Let's take a look at one of these boxes. Person A box. This is Alice's simple box, if you will. What's in here? Well, this is a type of simple box, and it's using, here's the box object. Ooh, what's going on here? Curve 25519 and salsa 20, poly 1305. Curve 25519 is a asymmetric crypto system. It uses a mathematical technique called elliptic curves, and you can you can go find it on Wikipedia. So you're welcome to go read up on what elliptic curves are and what they are if you would wish. Okay. Who made curve 25119? It was defined by Diffie-Hellman. And Bernstein has since, all hail our Lord, DJ Bernstein, has since proposed the name curve 25519 for the underlying curve and the name x25519 for the function itself. Okay, so it has the blessing. Curve 25519 has the blessings of DJ Bernstein. All right. Again, if you read these Wikipedia articles, it's really interesting. Remember I told you last week the symmetric key cipher AES? Some people have doubts about it because the US National Security Agency tweaked it a little bit before they made it public. Well, there was previously a symmetric key cipher, dual EC DRBG, also I guess a elliptic curve crypto system, where the NSA had again potentially implemented a backdoor to it. So we don't trust the government. We only trust in DJ Bernstein. Okay. All right. Okay. So what's going on here? Curve 25519 is the asymmetric cipher. I believe Salsa 20 we saw last week was Bernstein's preferred symmetric key cipher, and it's a stream cipher that he suggests you use instead of AES, because and AES is a block cipher, but he says that this stream cipher is much faster, so you can do more rounds of crypto and make it more secure. And then Poly 1305, if I remember correctly, was the block cipher that's used to create the MAC block, the message authentication code, the hash, to create the hash. All right. So box is basically using three ciphers: asymmetric key, symmetric key, and a cryptographic hash. And is using all those to do this big picture, right? Asymmetric key ciphers, symmetric key ciphers, but within this, if you remember my picture from the first slide or the end of last week, there's a hashing going on as well, a cryptographic hash going on. All right. Simple box and box. All right, cool. Question. With secret box, we had simple box, and the difference was you don't need to make a nonce. With box, we again have simple box variant. You don't have to make the nonce. If you can just use simple box, why would you ever use secret box or box? Like, when would you have to ever create the nonce yourself? Right? Because remember, even Bob, the person receiving it, doesn't need the nonce because the nonce comes with the message. It's just that Alice has to make the nonce. If we have simple box, why do we need secret box or box? The answer goes back to, let me see if I can find it. Last week's about two, not cryptographic problems, but two usage problems, two problems of practicing, two problems of applying these techniques. Scroll, scroll, scroll. One was called depth attacks, the other was called replay attacks. Okay. Depth attacks was the problem where two ciphertexts exclusive OR into the plain text exclusive OR together. And we said we can resolve that by adding the nonce, right? And here we don't need secret box because simple box can generate the nonce for us. And only Alice, the person sending the message, has to create the nonce. So simple box can do this. However, the other problem, the replay attack problem, that required another solution. Here, Bob, the person receiving the message, has to send Alice the nonce, right? This prevents Eve from just sending the ciphertext to Bob a second time. Because to prevent replay attacks, Bob has to send the nonce first to Alice. This is where, if you were for any reason had this problem, where you were afraid of replay attacks, you would need either secret box or box because you would need to give it the nonce that it should use. All right, the nonce that presumably comes from the other side, from Bob. All right, so it's to prevent replay attacks that we use secret box or box, because there you can provide it the nonce that you want to use. You wouldn't generate the nonce, it would probably come from somebody else. Okay. However, as far as I can tell, box and secret box, excuse me, simple box, if you just use simple box, you cannot really prevent replay attacks because once you've created the ciphertext, anyone can keep sending the ciphertext again and again. There's, you cannot prevent an attack, a replay attack. All right? But most of you probably don't have systems where you're afraid of a replay attack. But if for any reason you do, now you know you cannot use simple box, you have to use either box or secret box. All right, great. All right, that's how we use RBNACL to do asymmetric key cryptography. All right, you can generate keys and so on and so forth. I don't remember, but I think this was maybe one of the articles I sent you was about the NaCl monoculture, right? And I was asking, do we really want to just use whatever DJ Bernstein gives us? Do we really have this much faith in him, right? And I sent you articles where people said, you know, so I don't know if I sent you this, or maybe I haven't sent these articles to you. Have I sent these articles to you about BitCrypt and stuff like that? No. So BitCrypt was a malware that encrypted your hard drive and then blackmailed you and said, pay us money in Bitcoins, and if you do, we will send you the key and you can decrypt your hard drive again. Okay, it was a malware. Um, Luckily for us, the people who made the malware made a slight mistake. The key they were using was only 128 digits long. And it turns out, and they were using RSA, public key, crypto. And it turns out people were able to break the keys under 48 hours for any given key. So if anyone was like hacked and by this malware, cryptographers could help them with sufficient computing power to retrieve the keys within 48 hours just mathematically. Okay. So good thing that some malware developers also don't know how to use crypto because they should have been using DJ Bernstein. but but this article, and I'll send you this article. It says this is a problem not only for malware but for good people as well. We all don't know how to use crypto. Like if you were just using RSA, you would probably use the wrong size key or some other problem. All right. And they said that there's just too many parameters to pick. All right. And they end up suggesting just use NaCl. It's an opinionated library that do everything correctly. Curve 25519 for elliptic curve asymmetric encryption, Salsa 20 for symmetric, Poly 1305 for master's authentication. All right. Why is this better? First of all, because it's not designed by some government which may have an incentive to give you a cipher that they can break. All right. One of the leading names in security, Bruce Schneier, I think his name will come up more and more as the semester progresses. You can read about him. He's a cryptographer and a public thinker about cryptography, probably one of the best we have in our generation. And he said, I no longer believe anything that the NSA or the government has touched. All right. Um, and as of 2013, he published an article saying the US spy agency, Information Intelligence Agency, is likely breaking almost all the encryption on the internet by themselves. They can probably do it. But that was a long time ago. So since 2013, you will see that most of the protocols out there are using DJ Bernstein's ciphers. HTTPS, SSL, TLS, all of the stuff is using DJ Bernstein's ciphers now. We trust him more than we trust the government. Okay. And also the beauty is that his ciphers can actually encrypt more information than traditional techniques like AES, right? Even though there are traditional ciphers that we still do trust, DJ Bernstein ciphers can process a lot more information in a shorter period of time. So it's just also more efficient.
But like in that sense, is it trust? We don't need to trust him. We can show that it works.
Well, first of all, the ciphers are open source, so all the mathematicians in the world have a fair crack at it. All right. The only difference is we believe, as long as we don't find out that DJ Bernstein was a government agent, we believe that at least like no particular source has manipulated the ciphers. All right. And as of lately, you'll find that more and more companies and agencies are adopting DJ Bernstein ciphers into their own suites. So in 2014, the Chrome browser now uses, um, as part of the Android platform, the Chrome browser on Android, the HTTPS connections use, I think, Salsa 20, Cha-Cha, whatever, right? They use all DJ Bernstein stuff. Cool. Let's see asymmetric key crypto in practice. Do you remember in the beginning of the semester, if you hadn't already done it, you had to make an SSH key pair? Remember this? And you had to make a public key and a private key. And what did you do with the public key? You just gave it away. You gave it to GitHub, right? Didn't it feel weird that you're giving one of your keys away to somebody? It's the public key. You can give it to anybody you want, all right? So what you did was you used this command SSH keygen to generate um, the keys. Okay, I will mention something, and I believe it's on the if you go to Facebook, if you go to Facebook, that's the place to go for security, huh? But we can go to our security page, and somewhere here you have to search it. How do I search just one group? This one. Okay. And let's search it for SSH. Hold on. Okay, I'll try to post this online later. Um, there was an issue where SSH keys were for a supercomputing facility were stolen by somebody, and guess what they did with it? Bitcoin mining, yes. They use a supercomputing facility to harvest Bitcoins, cryptocurrency. And I posted in here a little story. Let's see if I can find all the comments. Oh. No, not this one. Oops, this is the wrong story. Wrong story. Back up, back up, back up, back up. Here we go. Oh, it wasn't me. It was a student from our class who posted this. Where basically people are being encouraged to upgrade your SSH keys. Consider upgrading them in these coming years. We've been using RSA, and we have reasons to believe that maybe within the next 10 years, possibly there could be a crack of RSA. And we are suggesting you move to, does that look familiar? Back to our elliptic curve 25519 cipher. There, so you can just search that group for ed25519 if you want to find out how to upgrade your keys. Okay, it would basically generate new keys for you, and you would have to distribute it to GitHub and whoever else has your SSH public key. All right, but when we created it, SSH used by default the RSA algorithm. All right, to generate your private keys. We told it to use a 4 kilobyte key, 4,000 bits, 4 kilobyte, 4,000 bits. Yeah. No. 4,000. No. 4,000 bits, not 4,000 bytes. Excuse me. 4,000 bits. Okay. Not kilobytes. 4 byte, whatever it is. Okay. And then what else happened? It said, oh, which file would you like to save it in? And then it said, please enter a passphrase and type the passphrase again. You remember this? You had to do this stuff, and blah 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 blah. And then it gave you something called a key fingerprint as well. Let's talk about all these things. First of all, what did it do? It generated two files. One was a public file with .pub, was a public file, and you can copy and paste this onto GitHub. This is my public one. And the other was a private key. You should never share this with. I'm not that stupid. Am I? Am I? Am I? Well, there's two things going on. First of all, is your private key just stored on your hard drive as a private key? Because anyone who can access your hard drive now has your private keys. That would be kind of crazy. Okay. Not to mention Dropbox has all your private keys then, right? If you, well, maybe this folder is not in Dropbox, but if you back it up, it's in your backup. The answer is actually no. This is not your private key. This is the encrypted version of your private key. And it's been encrypted using well, just take a look at the first few lines of the private key. It will tell you what it's used to encrypt it. In this case, it's used 128-bit AES in, does anyone remember this? Cipher blockchaining? In cipher blockchaining mode, CBC mode, not EVC mode or whatever it was called, the bad one, ECB. Don't use ECB ever. All right. So in CBC mode. So this is actually your encrypted private key, not your private key. I may have also changed the letters before I put it on a slide. Okay, so don't worry. Okay, so question. It encrypted this private key to store it securely. What key did it use to encrypt it? Yeah. Remember that secret passphrase you gave it? What do you think that secret passphrase does? It only does one little thing. It encrypts your private key using AES. That's all that key does. All right. It's not actually the key that's used to actually send information over the internet. That key is generated cryptographically. And actually, the key you entered here, the key you typed in, that's actually not the key. What it does, everyone should be doing, is it takes this kind of a key, like the password somebody types in, and it uses that password it passes it through another cipher or a hash, a cryptographic hash function like poly 1305 to generate the actual key with maximum entropy in it. Okay, it happens to be a deterministic process. So given the same passphrase, it can regenerate that key. All right. So that was the use of RSA. All right. So now, what is RSA? What is this SSH used for? One is to connect to places like GitHub without having to enter your username and password every time. It can authenticate you. Why? Because the RSA contains your public key and your private key. If GitHub wants to know who you are, it's just going to say, like, whenever you're like, git push to GitHub, GitHub asks Git, hey, I don't know who you are. Prove that you are Steven. Here, it'll give you some text or some information and say, encrypt that with Steven's private RSA key, which means sign it, digitally sign it. And if I can decrypt it with the public key that Steven gave me, then I know it's Steven. That's how GitHub knows your computer. That's how it authenticates your computer. All right. It basically challenges you to sign something with the private key of the SSH key pair. All right. Excellent. And now, and also, you also probably know that SSH is what you use to connect to another computer's terminal, right? You SSH into another computer to use the command line on the other computer, on the remote computer as well. Well, they're also using the same idea. They're using the private key, public key to get you to challenge you, to get you to sign something to prove who you are. That way, you don't have to use a username and password every single time. All right. What it means is that once on your computer, there is running at all times, I believe. Let me see if I can find it. There should be running at all times an SSH agent running in the background of the computer all the time. And that's what's handling these challenges and these requests. Okay. So GitHub, or when you SSH in, there's always an agent running that is doing all this stuff for you. And this agent, this is the risky part, stores the private key in memory while it's running. I hope it obfuscates it somehow, but the private key is kept in memory so that it doesn't have to, you're not always asked to enter your SSH passphrase, almost hardly ever, right? Because it keeps the private key in memory, which can have its own security implications. All right. Has anyone ever hacked that? SSH private key memory crack or hack? I don't know. All right. So that tells you about SSH and how that works. You've used that before, right? Here's something else that I want you to start using. And I'm going to ask all of you, as one of your assignments, to install on your computer if you haven't already. It's a very venerable piece of software. It used to be called, well, the protocol itself is called GPG. Yeah, the software itself is called PGP for pretty good privacy. GPG stands for New Privacy. What the hell is this? Guard. There should be a D at the end. TA. New Privacy Guard. Okay. New is kind of like this. I don't want to say organization, but a set of open source tools. All right. In GNU we trust. Yeah, that too. um, with the joke being that GNU stands for GNU is not Unix. It's like recursive joke. All right. All right. So this is a software that you can install on your computer that allows you to send messages to other people, allows you to encrypt and send messages to other people. Nowadays, it's less used because you can use things like Signal, Telegram, potentially even Facebook Messenger and WhatsApp. They all have end-to-end encryption, end-to-end cryptography. meaning that those companies themselves cannot decrypt what you're saying. But when Facebook tells you that, I don't know what to do with it. PGP is another one that allows you to do a similar thing. What does it allow you to do? So basically, you have to install a software on your computer. On Macs, it's called GPG Tools. On Windows, it's called GPG for Win. There might be another one, I don't know. On Unix, it's called GNU-PG. All right. And with it, what you can do is you can keep a record of all the public keys of people you trust. Okay. So I have on my computer a GPG keychain. And on this keychain, I have the keys of a lot of the previous students who've taken this class and others. Some of these keys have expired since, but others are still valid. Okay. Um, and in this keychain, so basically, if somebody sends you their, so using GPG, you can tell it, please generate a private key and a public key for me. And then it has functions by which you can say, give me the public key. And then you can just send the public key to whoever you want. Okay. One thing you'll notice, so for example, for me, I put my public key on my website. Okay. And yeah, popular courses, security is not here. Find me online, verify me. Here's my PGP public key. All right. Now, you are about to go and copy this and paste it into your GPG keychain, but then you're like, wait a minute. What if this isn't Somi Array? What if it's somebody else called Somi Array? What if somebody's hacked Somi Array's website and changed the key? How can you trust the key? We're now going to enter the rest of the semester where we'll discover that the hardest problem, the last mile problem in security is trust. All right. And how do you learn to trust is a problem. How can you trust that this is my key? What's that? Web of trust? Yeah, there's web of trust, which I'll try to mention if I have a second. The other way is this. You can take this key, or your GPG tools can take this key and hash it down into I give you a small hash of this and tell you, here's a hash of this big thing. And you can just see if the key that you're getting matches the hash. Ask Somia for the original hash. Okay. How do you ask me for my hash? You come to me and say, Somia, can I have your hash? And I say, yes, you can have my hash. I'm carrying it all the time with me. I am carrying it all the time with me. It's actually on my business card. And if you look at my business card somewhere, excuse me. If we go back to on my business card, I actually put what I call the fingerprints. I have my PGP key fingerprint right here. All right. So if somebody's really like, Somi, I need to know if that's your key, well, you've got to meet me in person and you've got to verify it's me. I hope you know me. And if you can verify it's me visually and I give you the card, my fingerprint is on the card. All right. So that's how I do it. Other people may do it another way. Yeah.
How was that for you during COVID times?
I cannot give people. I'm like, luckily, I didn't meet any new people in COVID, so there was that. No, but that's a really good point. How do you do that? Wow, trust is a problem. Trust is a real problem. All right, Google Meet, and I'm like, ugh. And Google's like scrambling it and changing it for me. I'm like, no, Google, don't do that. Or I have to read it out loud. 8542. And Google's using a deep fake voice of mine to change it. I don't know. It's very difficult. Trust is a difficult thing, right? So I'm going to ask all of you to please set up PGP, and you can also tell GPG, excuse me. Um, you can tell it, please export my key to a public key server. It's a function that it has. There's many servers around the world, and you can export your key to it. And that way, if I want to find you, I can ask my PGP tool, please go find so and so, and your email address will be the unique thing. I think that it'll track you by, and it'll say for that account, please give me the public key. So I trust it because I trust the PGP tool. The PGP tool creates what's sometimes called a web of trust. It puts all these keys on key servers that it trusts, and it uses your email and other things to verify that it's you. And so then I can go find you without having to actually go give you my card or anything like that. Okay. But after I found you, probably if it's something very sensitive, I would still say, hey, Ed, can you just tell me your hash, your fingerprint again, just to be sure? All right. I'm going to ask you to use PGP this semester to share secret credentials between each other. Like if you have some API tokens and stuff like that, don't just like line message it to each other. I mean, I swear in Taiwan, I go to startups and that's how they exchange keys. They like line it to each other. I'm like, oh, Jesus. You just need to lose your phone and then someone's got all the keys to your company. That's crazy. Please don't line it to each other. Use PGP to send encrypted messages. You can figure it out. You're all sophisticated people. All right. But while you're figuring it out, one thing you're going to find out is it's not super simple. Like you can figure it out, but maybe your grandmother could not figure it out, or your grandpa couldn't figure it out. Okay. Which means we do have a problem still in this world that asymmetric key crypto is so powerful, but it's very user unfriendly. And year after year, it's an open challenge to make a user friendly version of uh, public key crypto. Okay. One solution that I like is called Keybase. I encourage you to all to go to Keybase and try playing with it. Guess who bought Keybase? Zoom. After Zoom was attacked for not having end-to-end crypto, in fact, not even knowing how to do crypto correctly, like they had problems again with nonces or something weird like that. They screwed it up, and people were like, "You don't even know how to use crypto correctly." And then they quickly went and bought this company to do it for them. So I trust this company. They're really good. They do some risky things, like for example, they actually offer to store your PGP private key. I don't go that far. I don't give them that, but I give them a lot of other things. Okay. So one thing you can do with them, which is really cool, and I love this, is you can verify with them who you are using PGP. Okay. Basically, I don't give them my private key, though they offered to keep that for you, but I give them my public key, and then they challenge you. They say, okay, I'm going to encrypt something with your public key. You tell me what I told you. So you have to decrypt it and tell them. Okay. And they provide you some command line tools that will interface with GPG and do this for you. All right. Once it trusts you, it does something very cool. You can ask it to give you keys to verify your other assets. How do you know that my website is my website? Because actually, on my website somewhere, do I have it here? So what it does is it gives me some encrypted information and says, please post this on your website. So on my website, I made a file and I put some encrypted information that Keybase gave me. And they went to my website to see if they could find that file and decrypt it. And if it finds it, it then authenticates that somiarray.com really belongs to somiarray. We have verified it by forcing him to store something on his website that only he could have decrypted and stored. Similarly, I asked it to verify my GitHub by putting something on one of my GitHub repos that it could go look at and verify, only somiarray could have done this. Similarly, I did it with Twitter. You can tweet a little message that it'll give you, garbled text. You just tweet it, and it'll find your tweet and say, that's Soumya Ray, that's a verified Twitter account, et cetera, et cetera. So a very interesting bit of software that you can use. And also, once you've got it, you can then use it to do asymmetric and symmetric key crypto with your friends. So it gives you a messenger app that you can install that you can use to now talk to all your friends. All right. So either use PGP or Keybase. I suggest you install both and use that to exchange secret information. All right. All right. All right. Okay, question. Okay, PGP is kind of like the protocol and the technique. GPG is like the software tool. All right. What PGP does is actually the picture I showed you before. Remember this picture I showed you before of how to use asymmetric and symmetric key crypto? All this business that RBNSL does for you? PGP does the same thing. Here's their figure. When you want to encrypt data to somebody, it helps you generate a symmetric key. It encrypts the symmetric key using your public key, sends the encrypted key and the encrypted data to the other person, and GPG on the other side undoes it. It retrieves the symmetric key, it decrypts the symmetric key, then using your private key, and then uses the symmetric key to decrypt the data. All right. So it's doing the same thing that we've discussed using both asymmetric and symmetric key crypto. So when you send somebody a message with PGP, or GPG, or let's call the technique is called PGP. PGP doesn't actually tell you it's using symmetric key crypto. It makes it look like it's using asymmetric key, but it's not. It's doing what we're doing with box and simple box. It's using symmetric key crypto to do the cryptography of the data. It's just using asymmetric key, RSA in particular, I believe, to encrypt the symmetric key. All right. Um, okay. There is also, by the way, a GPG gem for Ruby. I haven't played with it much, but there is I have played with it a little bit. There's a gem called GPG Me, GPG ME, and that allows you to do GPG on your computer. It's of limited use because when it needs your private key, it has to ask you to enter your passphrase. And a window pops up and you've got to do this on your local computer. So it could be useful if you're creating some kind of command line tools that are using GPG. Okay. All right. And with that, we kind of conclude our cryptography section of this class. So we've done how many weeks of crypto now? 4 weeks of crypto, I think. We've done 3 to 4 weeks of crypto now. We did 3 weeks. We did a introduction to symmetric key crypto, modern symmetric key crypto, and now public key crypto. So we've done at least 3 or 4 weeks of crypto alone. Before that, we did basic information theory and error checking stuff. All right, so that we did a couple of weeks of that stuff as well. So now we have a lot of tools under our belt, and you understand a lot more about crypto than you probably did before you came to this class. Okay. Even if you know cryptographic algorithms, now you know how they're applied. If you know how they're applied, now you know how they work. So I hope to have covered all of this. And today we have learned some stuff that adds to our understanding of confidentiality using public key crypto. So you can use this technique to, again, remember, it doesn't actually encrypt your data, it encrypts its symmetric key. You can use digital signing to authenticate yourself to people, and that's how your computer authenticates itself to GitHub every time you do a git push. Okay? And non-repudiation as well. If you want somebody to, so my question earlier was, how can you tell a company that, hey, I got a receipt from you, but if the company says it's not my receipt, what companies should be forced to do, maybe at least online, is every time they send out a digital receipt, they should be forced to digitally sign it so that they cannot later repudiate, they cannot later claim it's not their receipt. All right. And if you ever have a system that needs this kind of non-repudiation, you can use digital signing for that. You can force people to sign it, and that way they can never say it's not from them. Because if they've signed it, anybody can decrypt with their public key and say, listen, it had to be you. Unless you lost your key, in which case that's another liability. I can sue you for that, maybe. I don't know. All right. So we're filling in all the boxes. We're filling in the boxes. And trust me, this is going to be jam packed by the end of the semester. We're going to have a lot more stuff to put in here. This is just the beginning. All right. But we've ended our discussion of cryptography. From next week, we're going to enter applying security to software developments. And for those of you who have taken my SOA class before, the next couple of weeks will be, a few weeks will be relatively walk in the park, cakewalk. Meaning it'll be simple because I'll cover techniques that I've used in that class, but I'll try to add some security content to every week as well, so it's not totally boring for you. All right. Okay, so from next week we'll start making our product potentially. All right. I'll send you some a homework assignment possibly, but also I'll send you an assignment asking you to refine your project ideas. I'll give you a description of that. Okay. All right. Thank you all very much and have a great, what is it, weekend.